current carrying wires are running parallel to one another. Well, I guess you could have two wires that are going in the same direction as one another. And if you zoom your eyes in on this here, can you see that there's current A and current B that are both going sort of down and to the right? I'm kind of pointing at the I vectors right now. Whereas over here, I've got current B going down and to the right, or current A going down and to the right, and current B going up and to the left, I guess, right? So they're going opposite directions. And then down below, looking from a different perspective, stolen from a different textbook, we've got two wires that are going in opposite directions and two wires that are going in the same direction. And I guess as I'm thinking about this, I probably could reorganize things because that's an illustration of that one and that's an illustration of that one, if you can see what I'm talking about, right? So like I got a little bit of a page layout issue going on here. But according to this second textbook, and actually according to the first textbook too, but the second textbook says that wires going in opposite directions will be repelled by each other, and wires that are going in the same direction are going to be attracted to each other. The one up here says it as well, except that it actually draws hands in and talks about the forces acting on them, fingers being magnetic fields and things. And I feel like there's enough going on here, and it's three-dimensional enough that we need to unpack it. We need to actually draw the picture, because I would hate to just give you a thing like this and say, oh, do the reading, understand it. So let's take this. How do we do this? Let's do this picture. Let's do the one where they're going in the same direction. Let's try that, okay? All these different flow arrows. We'll have two current carrying wires that are going in the same direction as each other. And I think I actually like the style of art from the bottom pair of pictures the best, just because it's nice and simple. We'll say that there's a wire coming at us. And so the dot indicates the flow of current. And we'll draw it like a cylinder so that it's a wire with current flowing towards us. And we're going to call them current 1 going in this direction and current 2 going in this direction. But something that we know about current 1 is that since it's a wire and it's got a magnetic field around it, since current is flowing, according to Ørsted's discovery, that first right-hand rule, we would have a magnetic field around this wire. And so what I think I'd like to do is draw, we got it in this diagram over here as well, I'd like to draw that magnetic field as a dotted line, a circle. Okay, so the circle would be around this wire. And if you really are a three-dimensional thinker, it wouldn't just be a circle. Wouldn't it be like a contour that projects backwards into the page as a cylinder, right? So there would be a magnetic field that's particular strength at that distance away from the wire. And in terms of the orientation, you can pull your own right hand out. If there's current coming out of the page, then the magnetic field would orient upwards on the right-hand side, and it would orient downwards on the left-hand side. And you can check, see the little schematic we had up above, that agrees with that idea of the right-hand rule. Now, the other thing is, and this is where I feel like the diagram up above kind of lets us down, we should extend the magnetic field out and say, hey, at a distance further away, let's just draw a circle. And I'm going to be really intentional about the circle, so wait until I'm finished before you draw yours, okay? I'm going to draw a circle, and I'm specifically drawing my circle so that the circle around wire 1 intersects with the center of wire 2. You see what I mean? In other words, this dotted line is the magnetic field caused by wire 1, but we're also talking about that magnetic field as it's located at the position of current 2. Okay? So current 2 has a magnetic field going through it due to current 1. What that means is that at the position of current 2, there would be a magnetic field oriented upwards at that point in space. And so I'm going to call this magnetic field 1. You can put a vector over it, but it is upwards, okay? Then I want to think about current carrying wire number 2. Current carrying wire number 2, of course, has a magnetic field around it. And of course, magnetic field around current carrying wire number 2 is going to be downward facing on this side of that dotted line circle, upward facing on this side, and we can check the schematic above to make sure that we've got that right, or you can use your right hand for the first right hand rule to make sure that this is the case. But then again, I want to be intentional. And this is starting to look like some sort of crazy Venn diagram or something, but it's not. We're just mapping out the magnetic field lines due to two current carrying wires in the presence of one another. And I'm trying not to blot out all of my I's and my B's. But what that means is that the magnetic field is going to be downwards on the left as a result of current carrying wire 2, which means the magnetic field at the location of wire 1 is going to be downwards at the left and to the left. Sorry, downwards on the left. So we'll call this magnetic field 2. Now, in terms of like how far away we are from the wire, there actually is a distance here, right? So we would say that these guys are a distance r apart. And we could talk about it as either R1 or R2 because they're both mutually a distance of r apart. But when I go to talk about this in terms of forces, because of course if there's a current in a magnetic field, I'd want to talk about forces. And according to these diagrams up above, we've got, well, the claim is that they're forced to be attracted to one another. So if I take my right hand and I say, okay, so the current's coming out of the page, and at the location of wire 2, the magnetic field is oriented upwards. That means that that wire is going to get pushed to the left. And I can come in here and I can add in. I'll do it as, you know what, just so that it pops, I'll do it as a pink arrow. You do you, though, okay?
Sorry.
Yep.
Just right above that arrow in between the two lines, is that another arrowhead or a V?
Oh, no, that's an arrowhead. Sorry. That's not a V, it's an arrowhead just above that line. It's the radius, it's the distance between them. If it feels better to white out that arrowhead, now that we've developed our picture, I can white it out. Is that better? Yeah. Then we don't think there's like a velocity or something there or something? Yeah. All right. But if I take my right hand rule, I've got my magnetic field oriented upwards for the wire that I'm pointing at right now. The current is coming out of the page. There's my thumb. And so that wire is going to get pushed in the direction of my palm. That is to the left. So I'll add it in with pink because I feel like we got a lot going on here. Now, if I was going to label this up, I would probably call this the force of 1 acting on 2. But then I would also have a force over here that I would call a force of 2 acting on 1. Because this attraction is mutual, it's really a Newton's third law outcome of electric and magnetic interactions, okay? So let's make a quick little claim, and this is messy. Admittedly, this is messy, but if it took me 2 textbooks and a conversation to explain it, it's probably kind of like visually complicated, right? There's no math here or anything just yet, but we could say that 2 current carrying wires with a collinear current, that is, they're traveling in the same direction, parallel to each other, placed near each other, will attract. Now, something that I notice when I look at, and you can get those words in just a second, I'll uncover them again. Something that I notice about something like this, you notice I got these coils, these solenoids. Can you believe that on one side of these solenoids, so I'll make a little mess of my thing, if the current comes in on this side, there's a dot, and it goes away from me on this side, comes towards me on this side, and away from me on this side, would you believe that all the current on the right-hand side is going to be going in the same direction as itself? In other words, the current is going to go away from us here, 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 all the way down. What that means is that this coil is going to do what? Is it going to contract or expand? What do you think? Yeah? It's going to compress, yeah. It's going to compress. Would you believe that with AC current, when the current's flowing, You know, AC current is current that's alternating in its direction, right? And in North America, that alternating happens 60 times per second. And would you believe that 60 times per second the current goes this way and then it goes back the other way in our transformers, our electrical transformers? You probably see them in gray boxes or green boxes around your neighborhood, okay? City owned. So these things are the current's gonna go one way, then it'll come to a full stop and very quickly go back the other way, 60 times per second. That means that when it's flowing one way, this thing is gonna contract. When it turns around and flows back the other way, isn't there gonna be a moment in time where it relaxes? Right? When it comes to a stop, it's going to relax. But what that means is the back and forth means that your electrical box, your transformer in your neighborhood, I know it used to be on the front yard of my parents. I don't know if the house was cheaper because they got a big green box in the front yard or whatever, but that green box was home base for hide and seek, for tag. I won't say it was a fort, but kids congregated at that green box instantly. Neighborhood popularity. You know, you got a green box in your front lawn. Probably knocked the value of the house down, but whatever. We all hung out on that green box in the summer, in the winter, whatever. It was a meetup place. But what I distinctly remember about that green box, and you might remember it too, because I see like some nods around the room. Yeah, the green box, depending on your neighborhood. But the green box hummed, always hummed. It's because these coils are in there. And because of the 60 hertz frequency, these things are always contracting, relaxing, contracting, relaxing. That's the hum. Like this physics was always around you, okay? This was always happening. And it's because the wires are going in the same direction. All right, so if I was going to simplify the picture, though, the simplified picture, let's just call this a Newton's third law picture, because that's what it is. It's Newton's third law. It's just the origin of the forces happens to be electromagnetic. We would have a current, and now I'm not trying to be too three-dimensional. I'm just looking at them as end-on wire faces that are directing towards us. I1, I2, I would have B1, magnetic field 1. I'd have magnetic field 2. I'd have, and this is feeling like a free body diagram, isn't it? Force of 2 acting on 1 and force of 1 acting on 2. But if I extend it out to the electromagnetic coils, to solenoids, and I incorporate the idea of AC current, these things are going to attract intermittently, relax, then attract again. Okay, and that's the hum of the solenoid, of the transformer in our electrical boxes. Anyway, a little quick note here. You should know how to relate this to the third right-hand rule. Remember, the third right-hand rule is the idea of the motor principle. And so that's what we're talking about right now with that force. Also, to contracting solenoids. And I'm going to say, and be able to use this method to explain why opposite current flow directions repel. Okay, and just to get you started, because I'm not going to hold your hand through this one, I'm talking about current 1 coming out of the page and current 2 going into the page. And of course, that means that current 2 will have a magnetic field that orients upwards on the left-hand side, and current 1 is going to produce a magnetic field that operates, not downwards. Oh my goodness, I almost foiled my plans. Also upwards on the right. And if you're not quite sure why magnetic field is upwards on the right, go back to this method of thinking to figure it out with your right hand, okay? But I'm not going to hand hold you through this one. I want you to be able to reproduce the thought process, okay?